All right, so now how do we construct such a decision tree? First, let y bar be the observed mean of all outcomes, right? Now, the residual sum of squares for the whole data set is going to be the sum of y bar minus yi squared over all the observations. Okay, so in our case, this is going to be 120. So I just calculated it. I inserted some R codes for you just to make it clearer, because you can read how this is calculated, and you can probably understand it better rather than by my explanation. Okay, now suppose that we had just one split decision tree, right? So if the heap size, suppose that what we had is just like this, right? So we look at the heap size. This is our first split. If it is less than 35.25, then we go to the left. If it is more or equal than 35.25, we go to the right, right? And then we just make our prediction. In this case, our prediction is 18.08. In the case of no, it's going to be, of course, a little bit bigger, right? Which makes sense, 18.84, right? So because the body mass index should be an increasing function of the heap size. So bigger heaps means heavier, means higher body mass index, right? And on the left, all the about 80%, so 80.62% of all the nodes are there, and on the right, 19.38% of all the nodes are there, right? So this is the first split of our decision tree. Okay, now if this were all that there is, so if we did not continue, right? So it means that in order to calculate the new residual sum of squares after making this split, right? So we would take all the nodes on the left, so use this number 18.09 as prediction. So this is like the new, well, y bar for this region, so probably for the first prediction region. And for the right, so we would use the number 18.84 as the new y bar for the other region. And then we would calculate the total squared error, right? So in this fashion. Right? So we would take separately the sum for all playmates whose heap size is below the given threshold, and for those whose heap size is equal or above the given threshold in the training data, right? So this is the training error, by the way. So maybe this is the training error. So this is essentially the total squared error. So you divide this by the number of iterations, you get the mean squared error. Okay, so here is how we calculate the new residual sum of squares after making the first split. And the new residual sum of squares is 106.221, right? So, and this is, of course, smaller than the original one, 120.0262. Now, imagine that hypothetically, what if we made a different split? So instead of the split that actually is a part of the final tree, so we made a different split. So we made a split according to the height. So if the height is less than 67, we go to the left. And if it is not less than 67, we go to the right. We could do it, right? So hypothetically. But if we do it, then the residual sum of squares for this alternative hypothetical split is going to be higher. It's going to be 114, right? And this is bigger than the residual sum of squares of 106.221 that is actually a part of the final tree. Now, the way decision trees work is that they sequentially choose the split that leads to the greatest reduction in residual sum of squares. And this is called recursive binary splitting. So why is it recursive? Because basically we begin with the first split, right? And then when we kind of go to the left, so we just take a subset of our data. So initially we have like a big data set. So when we make this split according to the heap size, it means that some observations are going to, so we are going to split it into two parts. So those where the heap size is below the given number, is less than 35.25, and those where it is bigger than or equal, right? So, and some of them go to the left, some of them go to the right, right? And this becomes like the new data set, and this becomes like the new data set for a different tree. And we just continue applying the same procedure in the same fashion to subsets of our data set. So, and we split in it further and further, right? So like probably the one that is on the right, so we split it more or less evenly. So one goes to the left, one goes to the right, and that's it. So this is where we make our prediction. And here we kind of split it. And then we continue and continue and continue. Now, while doing this, we control for the number of observations in each decision region, right? So every time we make a split, we make sure that the number of observations is not below a certain threshold. So the default value in the library R part that I'm using, that I've used for this lecture, R part, is 7. But different are libraries for constructing the decision trees. So there are several of them, so they probably use different the default values. So this is not hard set in stone. And this can be easily controlled. So the tree stops growing when it is impossible to make a new split. Right? So basically, when it is impossible to either, so the residual sum of squares always drops. So if you make any split, any random split, it cannot grow, right? So it can only decrease. But if it decreases just like a little bit by, I don't know, a fraction of a percent, then we do not make a split. So there is another condition here, is that in order for a tree to grow, so every time we make a split, so the reduction in the residual sum of squares should be kind of sufficient. So at least, I don't know, I don't remember the default values, probably should be at least 99% of the residual sum of squares before the split or something like that. All right, so if the reduction is super minimal, then we do not make a split. And also we do not make a split if if a hypothetical split leads to a too small number of observations in a new decision region. And then, so when we cannot make a new split, we just stop growing it. So now this is what it looks like if you print the decision tree, so rather than plot it. So notice that in this is basically the same thing as a plotting, so only it has a little bit of more information. So this deviance here is actually the residual sum of squares, residual sum of squares. Right, so notice that this is the number. This is the total residual sum of squares initially, so for the root. Now, the first split is according to heaps. So where can we see it? So observations for which heaps are below 35.25, so this is this part of our decision tree. All right, so they live here. And observations for which heap size is above, they live here. And so it is this part. So basically, if this is part A and this is part B, then this whole thing is part A and this is part B. All right, so residual sum of squares are written here. So and the residual sum of squares after the first split is going to be the sum of these two numbers, right? So because it prints different residual sum of squares for the left and for the right parts of the split, right? So the 81.51 whatever plus the other number is 24.70 whatever. So this is going to be precisely this number. This number here, the residual sum of squares after the first split. Yeah, you can check it, 106.221. Okay, now hypothetically we could use this printed version of the tree instead of the plotted version of the tree to make predictions. So like, I don't know, so if say, I'll give you an example. So let's say heap size is 36 and height is going to be 70. So 70 inches is quite tall. It's 178 centimeters. So heap size 36, right? So we check where we are. So we look at this, at the first split. So is heap size below 35.25 or equal or above? And the answer is equal or above. So we are here, right? So new observation belongs to this branch of the tree. So then we check the second question, height. Is it above or below the given threshold, 69.25? And the answer is that it is equal or above. So which means that we are here. And we see a star here, and the star means a terminal node. So star in this printed version means a terminal node. Terminal node where we make our prediction, right? And the prediction is y-val, the predicted y-val, and this is our prediction. Well, at the same time, so we know that there are 10 observations in the training data that belong to the same decision region or belong to the same terminal node that as our new observation, and that the residual sum of squares for these 10 observations is this number, right? So if we constructed, so the training error for just these 10 observations that are in this node is this number, 3.868775. Okay, now decision tree gives us a way to measure variable importance, right? So every time we make a split, so we can compute how much the residual sum of squares dropped, right? So every time it becomes smaller, and this total drop in RSS due to splits in each variable, it gives us a very good measure of variable importance, of how much each variable influences the final decision, right? And this can be used for feature selection. Of course, it doesn't really make sense for two variables, but if you have hundreds of variables and you construct a decision tree, and if it is a huge decision tree, so you can just, I don't know, select variables whose importance is above a certain threshold, or just, I don't know, top 10 most important variables, something like that. So this is the end of the second part. So please do the quiz.